Hello and welcome back to CMOS RF integrated circuits. Today is the 29th lecture and we were discussing oscillators, and as part of that discussion today I plan to talk about noise in oscillators. So, in the last class we saw a couple of oscillator architectures, right, and these are fairly standard architectures. This kind of an oscillator is used almost all the time in RF CMOS circuits, CMOS radio frequency circuits. These oscillators are used all the time. The quality factor of the inductors, of course, is not terribly high. You get on an integrated circuit, you will get a Q of 5, little bit higher maybe depending on how high a frequency you are planning to oscillate at. The frequency of operation is typically decided by the resonance frequency between the inductor and the capacitor, right. So, remember the half circuit, right, how we went from the full circuit to the half circuit. Where was that? We did that over here, right over here, right. So, L and 2C are going to resonate, which means that the resonant frequency is going to be 1 by square root of 2 L C, that is omega, and then this divided by 2 pi will give you the frequency in hertz. Fine. Now, if you are planning to oscillate at a particular frequency, you do not exactly have too much control over the value of the inductor, over the exact value of the capacitor, right. I mean, you lay out some capacitor, and unfortunately because of parasitic effects, because of process variations, temperature variations, the actual value you finally end up with is going to be somewhat different from what you wanted to start with. Similarly, the value of the inductor is also not well controlled. So, the actual oscillation frequency is not necessarily going to be the frequency that you want. So, if the tolerance on the capacitor is 10%, if the tolerance on the inductor is 20%, then the actual frequency is going to be 10 plus 20, actually a square root of that. So, 15% in error. Now, that is a lot of error for a frequency. If I pick up, remember our discussion on the precise frequency, etc., etc. If I pick up a quartz crystal oscillator, the error in the frequency over there is 10 parts per million, right. 10 parts per million is something like 1 in 10,000, no 1 in 100,000. So, that is 0.001% in error. So, for a quartz crystal, the tolerance in the frequency is 0.001%. For our LC oscillator, it is 15%. That is a huge amount of error that we have to deal with. So, what is the solution? The solution, of course, is not to have an oscillator like that. Let us make an oscillator that is controllable. So, if somehow I can vary this capacitance value, suppose I am able to vary this capacitance value, okay. If I can vary the capacitance value, I can cover a large range of frequencies, and one of those frequencies will be the one that I want. So, this is basically the idea. Instead of being able to oscillate at a specific frequency, I will make a variable capacitor over there, and let us find out, let us turn the knob over there and figure out exactly, let us tune the oscillation frequency, right. So, this is standard. How do you tune this oscillator? Now, in the old hand tuned radios, you remember there used to be a radio, even a 2-in-1 box like this, and there used to be a knob over there. This knob was basically tuning the frequency. It is tuning this particular variable capacitor, because you do not know what the value of that capacitor is. It has to match to the value of the radio station, to the frequency of oscillation has to match the value of the frequency of the desired radio station. So, that is why you are tuning it and adjusting it and catching the precise radio station. You are listening also. So, there is some sort of feedback, and when you get the loudest noise or when you get the clearest sound, that is when you stop tuning, right. So, even older radios, there used to be a coarse tune, fine tune, etc., etc. Right. We do not want to be tuning this by hand, especially on a cell phone. You do not want to tune the receiver by hand. There is no knob. You want to do it electronically, and more importantly, you want it to be seamless. That is, you want it to be controlled by the base station. The base station asks you, go to this frequency, and you should immediately go to that frequency. There should be no such tuning business. So, to start with, this particular capacitor should be able to vary electronically. So, we use a voltage control. We want a capacitor whose value can be controlled by a voltage. Okay. So, this becomes a voltage controlled oscillator. The capacitance value depends on the voltage. So, as a result, the oscillation frequency depends on the voltage. All right. How do you make a capacitor whose value changes as a function of a voltage? Well, one of the easiest ways to do this is to actually use p-n junction diodes. What is a diode got to do with a capacitor? Well, the symbol is actually like this. We call it a varactor, but it is basically a p-n junction. So, let us understand this first. First, we understand that at DC, the voltage at these two nodes is VDD. What that also means is that even if these two voltages are varying, the average value of the average voltage at these two nodes is VDD. Okay. If you look at the average over time, value is VDD, exactly equal to VDD because of the inductor, right. So, if I have V control as any voltage between ground and VDD, which is usually the case, so V control is a voltage between ground and VDD. What does it mean for this diode? Is it forward biased or reverse biased? They are both reverse biased. All right. Now, think about what happens when you make a p-n junction. whenever you make a p-n junction, even before you apply a reverse bias voltage, let us say the voltage you have applied across this is 0 volts. Even at that situation, what is going to happen is that some holes from the p side are going to recombine with some electrons from the n side. Rather, some free electrons from the n side are going to diffuse across the junction and are going to fall into the holes that are there on the p side. Okay? And this happens along the junction, and what you are going to find is that along the junction there is some region where there are no free carriers. This is called the depletion region. All right. So, this happens even without applying any voltage. So, you have formed a depletion region. Now, there are no carriers in the depletion region. What this means is that that particular region, the depletion region, acts like an insulator. Right? You can't have electricity going, you can't have electrons moving across the depletion region, right. There are no carriers in the depletion region, no carriers allowed. As soon as carrier comes in, it falls into a hole, or it falls into an electron recombines with a hole. So, no carriers in the depletion region. This means that current can't flow through the depletion region. So, the depletion region is like an insulator. So, what we have over here are two regions that are full of conductors. These are all full of conductors, free conductors approximately, which are separated, these two regions are separated by a depletion region, which is like an insulator. So, whenever you have two plates separated by an insulator, this is some dielectric in between, it is like a capacitor, all right, and the capacitance is A times epsilon divided by D, where A is the area of the two plates. It is parallel plate capacitor. This is a classic parallel plate capacitor. All right. So, the capacitance is a function of the distance between the two plates. Now, when I reverse bias this, let us say I make this minus 1 volt. So, this portion is 1 volt, the N side is 1 volt above the P side. So, N side is positive. What happens? The electrons get sucked or get attracted towards the positive voltage, and the whole side is negative, the P side is negative. The holes, which are positive charges, get attracted towards the negative voltage. So, effectively what happens is that the depletion width increases. So, the more you reverse bias it, the more is the depletion width, right. So, if you reverse bias it more, D increases. If D increases, the capacitance decreases. Agreed? So, there you are. We have got a capacitor that is a function of a voltage. So, the capacitance is a function of how much you have reverse biased that particular junction. So, here we have 2 and both of them are identical. So, if I increase V control, if V control goes up, then the reverse bias decreases. If the reverse bias decreases, the value of the capacitance is going to increase. If the value of the capacitance increases, if the value of the capacitance increases, then the frequency is going to decrease. All of these are not proportional, right. So, the amount of capacitance is not proportional to the V control. So, do not even think that it is a proportionality over here, no it is not. I am not saying that it is proportional, the frequency is not inversely proportional to V control, it just goes down as V control goes up. So, overall what you are going to see is, if you plot on the x axis you plot V control, on the y axis you plot the frequency of operation of this, then what you are going to find is that there is some sort of negative behavior. Okay. In any case you can't have V control more than VDD, right. So, this is basically the idea. Now, the other things that you have to take care of over here are first of all you need appropriate diode size. Secondly, you maybe do not want such a high variation in frequency. I mean this is the variation in frequency, maybe you do not want this much variation in terms of frequency, maybe you want some lesser amount of variation. In that case you put a fixed capacitor in shunt with this, you will get lesser variation in terms of frequency. So, your net capacitance is now the fixed capacitor plus the variable capacitor, which will reduce the control dependence of the frequency, right. So, there are a number of these ways. So, this is a commonly used technique, this is an analog voltage controlled oscillator. Popular modern oscillators sometimes do not use this analog control, a lot of times they use digital control. So, they are no longer voltage controlled oscillators, they will be a digital code controlled oscillator. So, there will be a digital code and that will switch some switches on and off, and as you switch some switches on and off you create more or less capacitance whatever you want over here, and accordingly the frequency of oscillation is determined. Okay. So, those are called DCOs, these are also quite popular. VCO is something age old, this is quite popular, used routinely. All right. Now, important, what is the noise in an oscillator? So, we have talked about noise in the past, right. We understand that the MOSFET has a lot of these noise components. There is noise because of the channel of the MOSFET, there is noise because of the gate of the MOSFET to some extent, right. There are other noise components like flicker noise or 1 over f noise. What is the noise of an oscillator? So, how we do this is as follows. Let us make an attempt. So, this is my standard oscillator, all right. And let us say that both of these MOSFETs under quiescent operation, they have a certain amount of GM. Let us use the extremely basic small signal model of the MOSFET. It's got there is GM and there is RDS, right. However, that is not really correct, right. There is CGD. Now, CGD can be lumped in to the discrete capacitors that we have got over there. So, CGD is really between these two terminals, and I can lump it inside the capacitances that we already have over there. So, I need not bother about CGD, right. What else is there? There is C gate to source. C gate to source is like a capacitor on the load. And if you recall the small signal half circuit model of this, then that also this particular node is actually signal ground, if you recall the small signal half circuit model of this, and there is a capacitor between the output node and signal ground. So, it is actually coming in shunt with C. So, I do not need to worry about CGS either. What else is there? There is C source to bulk, that is irrelevant because source is at signal ground, bulk is also at signal ground. There is C drain to body capacitance once again looks exactly like the load C. So, drain to body also looks exactly like the load capacitance, and as a result I should not be bothering about it. So, all of these parasitic capacitors are really not of much consequence. They can be lumped, all of them can be lumped inside these two capacitors, all right. So, then in that case our crude small signal model of the MOSFET, which is basically a GM and an RDS, actually not a bad one, it is quite a good small signal model. Okay. So, let us plug in that particular small signal model. Right. Also, you have to recall that the inductor is not a pure inductor, it is something like an inductor in shunt with a resistor. So, I am going to put all of that right over here. all right, and let us call this, instead of calling it R parallel RDS, I am going to call it R prime. I think that is what I did in the previous class as well. Okay. Now, the important part now is the noise source. So, I have got a noise source because of the channel. There is an additional amount of noise current over here. What is going to happen to this particular noise current? Right, this is the issue that is of concern right now. So, let us redraw our circuit in a simplified manner. So, I have got L to ground, R prime to ground and C to ground. C is not really the actual capacitance, it is the capacitance in shunt with all the other parasitic capacitors. I have got another C, another R and another L. All of these are to ground. Okay. And I have got this noise current source on both the sides as well. All right. So, this is my complete small signal model, and the way we deal with noise is that we take one source at a time and we add the effect of both together at the output. So, let us talk about what happens to V plus, and we are going to select one noise source at a time. So, let us first pick this particular noise source, call this noise source number 1 and let us call this noise source number 2. So, we will pick noise source number 1 and see what is its effect on the output. So, first of all, what do I have over there? I have V plus times 1 by j omega L plus 1 by R prime plus j omega C, that is the current. I am basically trying to write a Kirchhoff's current Kirchhoff's node equation for V plus. Okay. So, this is what I have got at that particular node, and if you examine the node V minus, then you have got more or less the same thing without the noise source. Okay. No, I am not yet taking noise source number 2 into account. We are going to use superposition later on. We will deal with noise source 1, then we will deal with noise source 2. That is the way you talk about noise, right. Great. So, we are interested in finding out V plus, right. You have got two equations, you have got two unknowns, you should be able to find out what is V plus and what is V minus. How do you do that? Well, it is not very difficult. You add the two equations, you have got V plus plus V minus times G m plus 1 by j omega L plus 1 by r prime plus j omega c equal to minus I n 1. Okay. And next what you can do is you can subtract the two equations one from the other, and you are going to get V plus minus V minus times minus G m plus 1 by j omega L plus 1 by r prime plus j omega c is equal to okay. And you can transfer one of these terms in common to the other side, to the right hand side. So, instead you are going to get okay, that is what I am calling Z over here. And then finding out V plus is a trivial affair. You add the two of these and divide net result by 2. Right. So, this is your V plus. What about V minus? V minus is also not terribly difficult. You subtract the 2 and then divide it by 2. So, this is because of noise source number 1. Now, because of noise source number 2, I will get basically a flip of signs. I will basically get more or less the same thing, just that this addition and subtraction will now become different. all right. So, this is what I am going to get because of noise source number 2. Now, what you have to do is you have to square both of these and add them, right. So, you have to square the contribution of noise source 1 to V plus, you have to square the contribution of noise source 2 to V plus, and you have to add these two squares. That will give you the mean squared noise voltage at V plus. Similarly, for V minus. So, let us do a squaring operation and adding operation just for to see for ourselves what is going on here. So, first of all, what happens to 1 by g m plus z times plus 1 by minus g m plus z. So, this works out to if I am not mistaken. So, the 2's cancel out, and this is what you end up with. Okay. And on the other side you get if I am not mistaken, this is correct. Yes. And this is what you end up with. Now, what I am saying is you add the squares of these two things. Right, and I n 1 squared is now going to be a mean squared noise voltage. I n 2 squared is also a mean squared noise voltage, and in the denominator I have got all right. Now, I n 1 and I n 2 are I n 1 squared and I n 2 squared are basically both going to be more or less equal, because they are coming from noise voltages coming from noise currents of two different identical devices. They are matched devices. So, the amounts of noise contribution from these two devices are going to be more or less the same. The value of this is 8 by 3 k T g m delta f if it is in strong inversion and saturation. Okay. So, that whole factor comes out, and All right. Now, the mistake that you have not pointed out, it is not really a mistake, it is just that there is some dimensional problem over here. I have G m and Z, but I should not really have called it Z, I should have called it Y. So, let me call it Y instead of Z. I am sorry over here, just call it Y instead of Z, still the same result. Should have pointed this out earlier. So, this is not really a mistake, this is just notation. So, I would rather call it Y. Y is what? 1 by j omega L plus j omega C plus 1 by r prime. This is Y. All right. So, this is what I have got over here. Now, important, the noise is a function of frequency. Surprise, surprise. It does not come to me as a big surprise, but so Y has got to be replaced by what you have over here, and that makes the noise a function of frequency. All right. Next thing to observe, what happens at the resonant frequency? What happens at the resonant frequency? So, let us say at the resonant frequency, not at the resonant, let us say that this G m quantity is equal to 1 over r prime, right. That was the case we started off with and said that we get beautiful sinusoid oscillations when this is true. When G m is equal to 1 by r prime, then the poles are precisely on the j omega axis, which means that I am going to get a beautiful sinusoid oscillation. All right. So, let us say that G m squared, or rather G m is the same as 1 over r. Do you get noise? Is this quantity of noise large or small? So, to assess this, what I am going to do is I am going to divide numerator and denominator by G m to the power 4. Okay, I have put modulos over there because really that is what it means. I mean, it is a complex number, you are squaring it. We should really be talking about the modulos over there. Okay. So, what happens in this case? So, this is what I have, y by g m is 1 plus a complex quantity, right. Now, at resonance this imaginary quantity is going to be equal to 0 at resonance. Agreed? At resonance this imaginary quantity is going to be 0, which means that all I have is this real 1, which means that I have got 1 plus 1 squared, which is 1, divided by 1 minus 1 the whole squared times some quantity 8 by 3 k T by G m delta f. This is the noise voltage, mean squared noise voltage at the output, which means I have got infinitely large quantities of noise at the resonant frequency. This is fantastic, right. This means that at the resonant frequency the noise is going to be amplified, small amount of noise is going to be amplified, and this circuit is going to oscillate. This is really something very, very nice that I have going over here, right. What happens if I am a little bit off from that resonant frequency? I will still see a very, very large amount of noise, right. I will still see a very large amount of quantity of noise. What happens, let us say at DC, omega equal to 0. At omega equal to 0, what have I got as far as y by g m is concerned? Y by g m is something which is infinitely large, 1 by 0. Omega is 0. So, y by g m is something which is imaginary, but infinitely large. Agreed? So, I have got a quantity over here which is infinitely large squared. So, I have got infinity squared, square of that. So, I have got infinity to the power 4 in the denominator. I have got infinity squared in the numerator, which means that I have got effectively infinity squared in the denominator, and which means that the noise at DC is 0. There is no noise at DC. So, there is no noise at DC, there is huge quantity of noise at the desired frequency of oscillation. What about at let us say infinitely large frequencies? At infinitely large frequency, omega tends to infinity, this quantity goes to infinity, right. So, again y by g m is j infinity, y by g m is j infinity, means again I have got infinity squared divided by infinity to the power 4, which means that I have got no noise at infinitely large frequencies. So, all this is wonderful. What this means is, if you plot as a function of frequency the amount of output noise that you are seeing, you will see that at DC there is nothing, at large frequencies there is nothing, and the amount of noise is infinitely large at the desired frequency of oscillation. Right, and then it drops off. Great. So, what this tells us is that this oscillator will work because of noise. right, because I mean let us say there is no startup, let us say we did not make GM more than 1 by r prime, right. Let us say GM is precisely equal to 1 by r prime, then the poles are precisely on the j omega axis. So, when the poles are precisely on the j omega axis, will the oscillator work at all? That was a question raised in the previous lecture, right. I mean the question was, if at all it oscillates, what will be its amplitude? Why not 0 amplitude? So, this is why it will not oscillate with 0 amplitude. It will oscillate with significantly large amounts of amplitude, even when r prime is exactly equal to 1 by GM. You will get perfect sinusoid oscillations, but because of noise. All right. Now, unfortunately, what this means for us is that the output of the oscillator will look like this. So, what you had hoped for was the spectrum of the oscillator to look like an impulse. Okay. This is what you wanted to make. Instead, because of noise, channel noise in the MOSFETs, I did not even talk about noise in the resistors, right, but there is going to be noise in the resistor. There is no real resistor over there, it is a resistor because of the losses in the inductor, but that will create noise. Losses in the inductor means that you have got noise over there. Anything which is lossy will have noise, right. So, this is what we have got. We have got a system which will show a response like this. All of this is really called phase noise. In a real oscillator, all of this extra stuff is called phase noise. Why? Why is it called phase noise? Because there is no noise in the amplitude, the noise is only in the phase. The amplitude is the amplitude of a square wave, there is nothing to be said about the amplitude. The amplitude is 0 and VDD, or the amplitude is the positive and negative rail, whatever it is, right. You have generated a square wave, there is no amplitude noise, there is only phase noise. All that noise is over here, all of this entire skirt is basically phase noise. So, this is a way of figuring out the phase noise in an oscillator analytically. What we just did in this lecture so far is a method of figuring out the phase noise in an oscillator analytically. Unfortunately, this method is not correct. So, here I am delivering a lecture, and at the end of the lecture I am telling you that all that I talked about in the lecture is not correct. This is ridiculous, right. The fact of the matter is that this issue of analyzing phase noise has been dealt with in several research papers, right. There are several techniques talking about how to compute the phase noise in an oscillator. Unfortunately, they all have some deficiency or the other. Now, you are going to ask, where is the deficiency in this technique? The deficiency in this technique is in the fact that we did a small signal analysis. The very fact that we did a small signal analysis is wrong because of two reasons. Reason number one, if the poles are on the j omega axis, then the system is marginally stable. You can't possibly be doing a small signal analysis with j omega, Laplace transforms and so on. That is number 1. If the poles are outside the j omega axis on the right half plane, then you have got large signal oscillations. Why are you even doing a small signal analysis? So, these are the reasons why this analysis is not correct. However, it does give an engineer intuition into what needs to be done to reduce noise, for example, right. So, this is the reason why we did this analysis. For that purpose, this analysis works, mostly it works. Okay. If you ask a simulator to simulate phase noise for you, even the simulator, there are some deficiencies in that also. So, there are a lot of issues with precise computation of phase noise. It is still a research topic. This is one way in which we can analyze phase noise. All right. So, with this I am going to close this particular lecture. In the next lecture, we will look at other different kinds of oscillators, and we are going to move on. Thank you.